Oh, right. We talk about everything in the universe today. That is right. The universe is so big. This is Live Life Better, and we are talking about that thing above us, in the sky, all around us. That's us floating in space. We bring on Brian Keating today. He is in charge of UCSD's astrophysicist?
He is an astrophysicist. I don't know if he's in charge of it, but he certainly knows his shit.
I feel like if he wasn't in charge of it, he was like pretending to be in charge of it and did a really great job.
He definitely has keys to all the rooms.
He has keys to all the rooms. Who he is. Yeah. He's a very, very smart man. Astrophysicists, they are doing incredibly cool stuff, observing space and finding out the mysteries beyond. I'm really fascinated by stuff like this because we really know nothing.
Nothing.
Very little. We're just guessing, you know?
Very little.
We know very little. Anyways.
And he almost won the Nobel Prize.
He did almost win the Nobel Prize.
But then he didn't.
He'll talk about that. That's got to be a sad deal. Hope you enjoy. Oh, yeah. Ooh, ah, ah. Ooh, chakalaka. Welcome to Live Life Better. This is Scott Eastwood. I want you to live the best version of your life. We're all human beings. We're all just trying to figure it out. Find something you love and chase it. Whoa, okay. Brian, thank you for being here. Thanks for coming to talk to us. Losing the Nobel Prize. That is the title of your book. A story of cosmology, ambition, and the perils of science, his highest honor. Why losing the Nobel Peace Prize? The Nobel Prize. Is it the Nobel Peace Prize or the Nobel Prize?
It's a Nobel Prize. It's the Nobel Prize specifically in the sciences, but maybe it applies to more than just that. Maybe even the Peace Prize. So
there's a difference. You're saying there's a difference between Peace Prize and Nobel Prize?
Yeah, there's actually 6 prizes that were under the Nobel name at one point or another. The Peace Prize is probably the most famous of them. And there were even prizes that were added after Alfred Nobel, who's the namesake of the award, after he died. So he had a will. He died in 1896, and he wrote a will just about a year before he died that specified where he wanted his war profits to go from. So he had made dynamite and patented the product dynamite and become one of the wealthiest people that had ever lived in the 1800s. And in 1888, he was wandering around Paris, where he was a visitor and loved Paris, and he saw a headline that said, Alfred Nobel, the merchant of death, is dead. And it described him as the person who had killed the most people in human history up until that point.
Jeez.
By virtue of dynamite and making landmines and underwater mines and things like that, and all sorts of life-taking supplies. And so, obviously, but he wasn't dead because he was reading the obituary. So it's kind of like Mark Twain when he read his own obituary, said, the reports of my demise are over-exaggerated. And so, too, with Alfred Nobel. But in truth, it was his brother. And his brother had just he and his brother had a falling out a couple of years earlier, and they weren't even talking to each other. And luckily, they just made kind of a rapprochement and got friendly again just a couple of weeks before the older Nobel died, Ludwig. So that's whose obituary it was. So they got it wrong. Can you imagine reading your own obituary and it's like describes you as a real a-hole? It's just a total jerk. Yeah. You killed Scott Eastwood. You killed more people in history. Maybe your dad did, but only in the movies. But instead, this obituary really caused him to reevaluate his life. I call it like a Christmas Carol or It's a Wonderful Life, where this guy sees what life is going to be like after he's gone, and he realized then and there he had to make a change and do repentance. His repentance was to take these profits after he died and endow this prize that would agitate the world towards peace, prosperity, inventions, creativity, literature, and science. And that's what the prize did for a long time. But with, as with many things that are 122 years old, they kind of get a little bit long in the tooth. And I think the Nobel Prize, in particular in the sciences, which is my domain of expertise, is more than overdue for a reformation. And so that was the spirit of the title in some sense. The other sense of the word is that I lost the Nobel Prize. So I was hot on the trail of winning a Nobel Prize.
For what?
For discovering the spark that ignited the Big Bang. So how did the Big Bang unfold? How did the early universe come about? I had created an invention in the early part of the 2000s to go after this very question using a telescope located at the South Pole. And this telescope can't see visible light like the Hubble telescope or human eyes are actually tiny little telescopes. They can't, this type of telescope, to see the signal of the Big Bang and this period that ignited the spark that exploded the universe into existence from nothingness. This discovery was made by this experiment that I called BICEP. It's at the South Pole. There's a picture of it on the cover. That instrument in 2014, on St. Patrick's Day 2014, released evidence that we had detected this spark that caused the universe to come into existence. And because of that, immediately we were whispered as, making one of the greatest discoveries, not just in science or astronomy, but in all of human knowledge. Some said it advanced the progress of human knowledge more than any other single discovery in history up until that point. So it was an extremely, monumental discovery, and I agreed with a lot of the assessment for it. And immediately we were put both under the microscope for possible mistakes. There were haters that didn't like what we were doing. There were champions that thought we had proven their pet theory of how the universe unfolded. And then there were, kind of just cautious observers questioning whether or not we had done everything right and dotted all the I's and crossed all the T's. But along the way, the Nobel Prize was never really out of our eyesight or out of our mindset. We, in acting or something like that you're familiar with, I don't think you set out your career, correct me if I'm wrong, to win an Academy Award. You wouldn't turn one down if you got one. But the analogy sort of stops at a certain point because just as, it would be foolhardy for you to tell a younger version of yourself, oh, try to win an Oscar because so few people can win it. Only one man wins Best Actor each year, right? And actress, et cetera. So on the other hand, the movie studios that you work with, they'd be more than overjoyed if you won an Oscar. And in fact, they want most of their movies except for, what's the latest, Fast and the Furious. I love those movies, but I was in one. Oh yeah, awesome, fantastic. So I don't think that in most cases that the goal of that movie is different than the goal of a movie like Gone with the Wind or something like that. One is for entertainment, and one is sort of is maybe should care more about entertaining people, but along the way they're seeking the adulation, credulity of this wider body that confers these accolades.
This being the science community.
The science community, exactly. So the analogy with the movie studios that you're familiar with are the science funding agencies, this university that we're speaking at today. They really do put pressure on scientists, especially young scientists, that you're almost not even. I even had one young lady who was an aspiring astronomer drop out of astronomy because she was told early on that if she didn't win a Nobel Prize, she really wouldn't count for much in science. And that would be like telling a starlet you're nothing unless you win an Academy Award. So the pressures were there, and I think part of the reason that the book was written is to sort of cause that reformation to happen, not in the scientific community, but in the hearts and in the souls of scientists, because we do become a little bit entranced by this notion of winning this. I always say there's more people that are on the space station every year than are living people that have won the Nobel Prize in physics. It's such a rare thing that it's natural that such people, just as they do in Hollywood, they get elevated to these godlike statures. And I think ultimately that's not congruent with the way that science should be done.
So let's get granular just for a second on what you did that was considered for the prize, right? So you're talking about the spark that possibly created the Big Bang.
Right.
How are you seeing that?
Yeah.
How are we looking back into the past?
So when you look at Tim over there, he's about 1 foot or 2 feet away. You guys are keeping your distance. You guys work really closely together, so got to keep your distance. But you're not seeing him as he is right now. You're seeing him as he was about 1 nanosecond ago. Because light traveling incredibly quickly, it actually takes about a nanosecond to travel every foot. So you can convert that to miles, and you can convert seconds to hours, and it comes out to be 186,000 miles per second. You might have heard that along the way. Or you might look at the sun and see the sun not as it is this second. But you know that sunlight travels, it takes about 8 minutes to get from the sun to the Earth, those 93 million miles. And it's the same math either way. The point being, when you look out into space in any direction, you're not seeing that object as it is now. You're seeing it so many light seconds away from you. You're seeing it so many seconds ago. If it's 8 light minutes away from you, you're seeing it 8 minutes ago. So too, if you look back where there's no sun, there's no Tim, there's nothing in your way, there's no walls, there's nothing. You're looking back to the beginning of the time itself, when the universe itself came into existence. So astronomers long have known that you could look back into space where there's nothing in your way, no stars, galaxies, planets, anything else in your way, and you'd be peering back to the beginning of when light itself was created.
But how?
Exactly. So the how is the big question, right? So how did the universe come into existence? The best answer to that question is we don't know. But you never make progress unless you try harder, right? So
Well, I mean specifically, how do you look back?
Oh, yeah. So you can look back right now to the beginning of when optical light was created using the two telescopes inside of your skull, namely your eyeballs. So eyeballs are little telescopes. They reflect and they refract light through tiny lenses onto detectors. And instead of like an iPhone with 1,000,000 megapixels or 1,000,000 pixels, you have trillions of cells in your retina that sense color and intensity of white and dark light and colored light as well. And so your eye is a little tiny telescope. It's called a refracting telescope. It uses lenses. You can either use a refracting telescope or a reflecting telescope. A telescope that is a reflecting telescope like we have on Mount Wilson in Los Angeles or in Mount Palomar in San Diego County. Those telescopes have enormous mirrors, 20 feet across. They focus light to detectors in the form of these CCD cameras. These are detectors that work at really somewhat cold temperatures, and they're ultra sensitive. They can detect several tiny little photons at a time. In our case, we were looking back from heat left over from the Big Bang. So the Big Bang was incredibly hot. All the energy in the universe, all the matter in the universe was essentially in a volume of space smaller than this room. And then at some point, astronomers believe it started expanding. And that expansion causes things to cool down. You ever spray your computer with one of those computer cleaners and the can cools down a little bit? I don't know if you guys dust around your house. I don't dust in my house, but nevertheless, if I did or when I did, the can gets a little cool. And what happens is as things expand, they cool off. It's a phenomenon called entropy. So you guys might have heard of entropy, high entropy, low entropy. When the universe goes from having very much energy compressed to a tiny amount of volume, and then it goes from that to an incredibly large volume, same amount of matter. The matter didn't get destroyed, or the energy can't get destroyed, even if the matter does. The temperature of the universe cooled off dramatically. And it went from being white hot, brilliant hot, hotter than the surface of the sun many times over, and it cooled off over hundreds of thousands of years into what we call microwaves. And microwaves aren't too dissimilar from what you have in your kitchen, except that they're wavelengths of radiation, what's called electromagnetic radiation, with wavelengths of a few millimeters to a few centimeters. So they're 1,000 or 2,000 times smaller than visible light's wavelength. That is the leftover heat from the Big Bang. So the heat has cooled off over millennia, over 13.8 billion years, 13 billion.
Where do you guys get that number?
So that number comes from observing. So I like, again, I'm going to appeal to your shamelessly to your Hollywood roots, right? So you look at a show like CSI.
Shameless, very shameless.
Yeah, it's better than me. I'm shameful. Yeah. So you look at CSI. You ever watch CSI when there's a dead body in a room? Mm-hmm. And what is the first thing they do? They take the body's temperature. Why are they taking the body's temperature? What the heck is that going to tell them? So what they know is that when the human body's alive, the temperature of the human body is 98.6 degrees Fahrenheit. All they have to do is measure the temperature of the room, and knowing what mostly the body is composed of water. And water is extremely well understood. So what happens is when you're alive, your temperature is 98.6. The minute you die on those shows, they measure the temperature. They know the cooling curve of water. So if the room is cooler than 98.6, eventually the body temperature will equilibrate to that exact temperature.
To the temperature of the room.
Exactly. So what we see now is we know the temperature of not liquid water or the human body. We know the temperature that hydrogen forms at. Okay, so it's much, much hotter temperature. It's thousands of degrees Celsius, not 98.6 degrees. And knowing the temperature which hydrogen forms at and measuring the temperature that the universe is today, so it goes from being, say, what we call Kelvin, 3,000 Kelvin. It cools at 3,000 degrees above absolute zero, and it's cooled off over time to be just 3 degrees above absolute zero. That means the universe is expanded by a factor of 1,000 in all dimensions. And that size and that expansion we can equate to how many years it's been expanding for. So we use the...
So space is a certain temperature. Which
temperature of space, yeah. So it's 3 degrees above absolute zero.
Okay.
It's minus 270 degrees Celsius is about minus 450 degrees Fahrenheit. So it's frosty, right? And that temperature is irradiated. It's like we're inside of an oven. If we go back in time, the oven gets hotter. As we go forward in time, the oven gets cooler. So it's like the dead body. The dead body's cooling off over a certain amount of time. Most of the universe the ordinary matter in the universe is composed of hydrogen. We understand hydrogen. It's the simplest element. We understand its properties very exquisitely accurately. So we've measured how old the universe is by taking its temperature, literally, just like those people on CSI.
So how do you know, though, if the temperature of space, has it reached three,
That's
plus 3
temperature.
degrees, right?
Yeah.
That's its current temperature, right?
And it can never get to zero. It can never actually cool to absolute zero.
But if we're looking at space and it's already at 3 degrees above Kelvin?
Yeah, above 0 Kelvin, yeah.
Above
3
0
degrees
Kelvin.
positive, yeah.
How do we know that it hasn't been at 0 Kelvin for, let's call it 20,000 years?
Yeah.
And then it, then it heated
Just
up
recently,
or something,
So in science, we make use of something called Occam's razor, which is basically saying that the simpler you can make your explanation, the better. And the simplest of all explanations that still can accommodate all the things you see is likely to be the accurate answer. Of course, if something was willing to play tricks with us and we're a simulation and some giant supercomputer, which we can talk about, then all bets are off. But going back 1,000 years, 10,000 years, 20, that's like a blink of a fraction of a cosmic eye kind of lifespan. The universe is billions of years old. So we can look at the properties of the universe by making use of that property I said before. When you look back in space, you're looking back in time. So you can look back at a distant galaxy and actually take its temperature. So you can measure the temperature of that galaxy using microwaves and radio waves, and that will tell you what temperature was that galaxy at when the universe was half its current size. And it'll be twice as hot as it is now. So we understand precisely what the universe is made up of in terms of ordinary matter. Turns out most of the ordinary matter in the universe, or all the ordinary matter in the universe, pales in comparison to the non-ordinary matter called dark matter. That we know almost nothing about. That's a story, but dark matter doesn't have a temperature, so it can be really cold and not interact with the matter that I'm describing now. So we measure the temperature by looking at distant galaxies. We can uncover what its temperature must have been, and we compare it to models and simulations and the theoretical understanding that we've developed by combining every branch of physics together into one overarching model of how the evolution of the universe has taken place. But in all that, it's like saying, what did you look like, a millisecond after you were born or whatever. Those questions make sense, and you've grown. You've seen those sketches where they say, like, some poor kid on a milk carton, right? They say, here's the last known picture of him or her at age 4, and here's what they probably look like. And sometimes they look pretty accurate when they actually do luckily find the child. But in most cases, you can get sort of an accurate example. But what you'd really like to know as a cosmologist is, like, what did that child look like when it was born? What did the exact moment of birth look like for the universe? And more than that, we don't understand I talk to my kids about, where do babies come from? We don't know where universes come from. That's the ultimate question. Studying everything else is like projecting forward what would happen if this kid looked like this, this parent looked like this, and that looked like that, and then white mother looked like that. But we still don't know what is the process like. What is the conception of the universe like? How did it come to be? We know almost nothing about that process.
So by looking back, what do you know?
Yeah. So we know in physics we talk about everything in the universe according to the laws of nature that we understand today. We can predict on a statistical basis what the universe was like back to about a second, maybe less than a second after the Big Bang. So in some models of the universe's earliest moments, the Big Bang happened once. It created one universe. It's our universe. And in that universe, we can go back in time from today, which is not, in July of 2018, but instead we can go back 13.82 billion years ago to time equals 0 plus 1 second. And we know everything. That's not to say we know everything in the sense that, like, I can tell you what you did on a Thursday 6 years ago. And we don't know that. We know statistically what was the temperature of the universe, what was the density of the universe, what physical laws were predominating in the universe, how many stars are there in the universe, how much dark matter is there, even things we don't know about. We knew how much there are. We know how much there are of those things that are unknown. So there are these known unknowns, unknown knowns, etc. We can go back to a second, but we're greedy because a second is kind of an artificial thing, right? It's like a heartbeat or whatever, but we want to go back to time equals 0. I personally want to go back 10 minutes before 0. I want to know what happened before the universe that we call our universe, before the Big Bang came into existence. That's the ultimate grand goal.
Can we see all the way back to the Big Bang, or are we deducing from as far back as we can see to the Big Bang?
That's an excellent question. So when we say see, it's anthropomorphizing. We're saying, like, what do we see with our eyes or our senses? We can't see, even in the sense of anthropomorphizing, which is totally fine. We can't see back any farther in time or farther back in space than about 500,000 years using light. So the light that produced the heat that I'm talking about today, that's now 3 degrees, that light started off 500,000 years almost after the Big Bang, a little bit earlier than that. But let's round up to 500,000 years.
380,000.
380,000 years. Very good. Yeah.
Did a little bit of homework.
Yeah, good. That's great. So if you try to go back to 382 billion years or whatever, you actually aren't learning anything new, because light is really scattering amongst the particles of electricity and magnetism that were existent back then. The analogy I like to use is, you guys are surfers, right? So you go out in June, there's June gloom, right? So you can't see beyond the cloud layer using your eyes. But if an airplane flies overhead, you can detect the presence of that airplane using your ears, or maybe if you had NSA technology, you could see vibrations in the cloud using microwaves and lasers and all sorts of crazy stuff. We want to see farther back in space, which, as I said, means farther back in time, or vice versa, actually. So we need something other than light. That's the premise. And what came upon me, thanks to the insights of theoretical cosmologists working before me, was that you could use gravity instead of light to measure what the properties of the universe were, going back to even the first trillionth of a second after the Big Bang. Not just the first second. The first trillionth of a trillionth of a trillionth of a second after the Big Bang could be made visible, sensible, using waves of gravity, not waves of light. And that's because gravity is the weakest force in nature. There's 4 forces of nature. There's electricity and magnetism. That's kind of familiar. Gravity is very familiar. And then there are 2 forces that operate only inside the nucleus. So there's those 4 forces, 2 nuclear, 1 electricity and magnetism, 1 gravity. Gravity is the weakest of all 4 of those. But in science and physics, the weaker something is, the more long range its impact can be. So light waves are weaker than nuclear forces, and light waves can travel across the entire visible universe. You can see a star on the other edge of the universe, or a galaxy at the other edge of a universe. But gravity, you can go even farther, because gravity is even less interactive, which kind of explains some things, again, appealing to your surfing backgrounds, right? So you guys surf, you know that there's 4 tides a day, too high, too low. Where do the tides come from? They come from the moon. So the moon's gravity on one side of the Earth pulls the ocean on one side, and that makes a high tide on one side. But it also makes a high tide on the other side, exactly out of phase, 180 degrees. So what does that mean? It means gravity goes through the matter of the Earth. So light can't do that. So if someone's on the moon, they're shining a laser beam, it'll just hit San Diego, it won't go all the way through to Australia or wherever's on the opposite side of us. But gravity will. So if you had a gravity laser and you could shoot waves of gravity, it would go right through the Earth. So we make use of the fact that gravity goes through everything. It's going through us right now. And if these theoretical physicists' predictions were correct, the waves of gravity that were released during this explosion that ignited the spark of the Big Bang, those would be visible today in the form of waves of gravity, not waves of light.
And that's what you were looking for in your book.
Yep. So that was the goal of the BICEP experiment and its later successor called BICEP 2. It was to measure the waves of gravity, how they interacted with light at 380,000 years after the Big Bang. So it was like trying to detect an explosion, not by seeing the light from the explosion, but seeing how the sound waves of the explosion affected the light that we see today. So it's multiple levels of abstraction. It's not. I don't try to water it down in the book. I want to explain it so people can have an appreciation for how significant the challenge is of trying to observe something that's unobservable by human sensation. And for us, for me, that meant that you could actually potentially see back as far as any force could do. Because I said there's no force weaker than gravity. We don't know of any force. There might be, but we don't know of any force. So that means you could never go back farther in time to actually time equals 0. But it didn't matter, because the same theories that said the universe began expanding at the speed of light or faster, they also predict concomitantly with them that the universe is not alone, that we're actually accompanied by perhaps an infinite number of universes, some completely different than our universe, some identical to our universe, some where you guys are the scientists and I'm interviewing you for my podcast. And so things are really kind of hairy when you include an infinite number of possibilities. That's called the multiverse. That is
we know that exists in science.
We don't know it exists. It's right now, it's not even, I wouldn't even say it's at the level of a theory. You guys heard someone say, oh, well, whatever, climate change, it's just a theory. Or you hear, oh, the theory of evolution, it's just a theory. Nah, that's not really true. It's more than a theory when you have scientific evidence for something like, say, relativity. The theory of relativity is not a theory.
Would you explain that?
Yeah.
Because I'm fascinated by the theory and I've read a little bit about it. But
yeah.
I want to hear from
Absolutely.
your...
Yeah. So when we say when we talk about something in science being a theory, it's more akin to saying having a set of mathematical tools that describe something that are backed by physical evidence. So you can have a theory for anything. You can say there's a purple unicorn sitting at the South Pole, and that's your theory, and that's what's spinning the world around.
Like purple unicorns?
I like purple unicorns. Yeah, I don't know what that
In this case, relativity.
Yeah.
What is the theory of relativity?
So the theory of relativity describes the interconnectedness of how an event in space and an event in time are related to each other, how cause and effect can manifest themselves, and how the speed of light constancy determines the limits of visibility for certain events. So nothing can travel faster than the speed of light.
How do you know that?
So we've tested it. We've tested with any known material particle. We cannot accelerate it beyond. We can get arbitrarily close to the speed of light. Namely, you can get to 99.99%. That's how, say, these particle accelerators.
We can actually do that.
Not with people, but with beams of material, particles of matter called protons.
How do we do that?
So those are these big particle accelerators. Do you remember a couple of years ago people were saying, oh, the universe could all be sucked into a black hole because they're going to make this particle collision at this accelerator called CERN, or the Large Hadron
particle, right?
Yeah, so that was the Higgs boson, right? So that was in the search to determine the particles that are responsible for what we sense as gravity and mass. They thought that by accelerating particles near the speed of light, those particles could create miniature black holes. And the miniature black holes wouldn't know they're miniature, or they only start off miniature and they get bigger and bigger every day. So, or they could get every day, every trillionth of a second. So they could actually become exponentially large in an infinitesimal amount of time. Ignore that. I'm just saying that accelerator is located on the border of France and Switzerland. They accelerate.
Did we ever do that? Did we ever actually?
Yes, we have particles. We didn't create black holes. No. So we have never done that, but we have accelerated using powerful magnets in a tube in a circular tube that's sucked out of all the oxygen that could possibly be inside of this tube 100 feet underground. They've accelerated protons, which are the building blocks of all atoms. Hydrogen is made of just a single proton, a single electron. They'll take some hydrogen gas, they'll zap away all the electrons, you'll be left with just protons. Those are positively charged entities. If you get another positive charge near it, you can accelerate it because like charges repel each other. And then once that starts accelerating under the force of electricity and magnetism, then you can control its orbit in a tunnel. And the faster it orbits, the higher energy it has. So the higher energy, the bigger the tunnel, the bigger the magnets, everything gets larger and larger. So this thing is like 30 kilometers around, I think. They accelerated these protons and their antiparticles, called antiprotons, to near the speed of light. I think it's like 99.94 the speed of light, such that they cross the border between France and Switzerland 12,000 times a second. And it's not just one of them. We're talking trillions of protons. If you were in there, you'd be like totally irradiated. You'd have like holes blasted through you, antiparticles. It would be really deadly. So you're not even allowed there unless you have a retina scan to go underground to see this stuff. It's really a fascinating place. This is really the biggest project human beings have ever built in science. It's not my project. It's a particle physics experiment. But you're asking about how do we know how fast we can accelerate stuff? You guys couldn't have gotten here. Well, you guys know your way here, but the fact that you were able to people are able to navigate using the global positioning system, the GPS satellites, they are built in for not only the effects of space, time, and for the speed of light, but also the effects of gravity. Gravity gets stronger the lower your elevation. So if you're coming from the mountains and you're coming down, from LA or wherever, and you came down to sea level here in San Diego, you would have to compensate for that, or you could be off by several feet, not like miles, but you could be off by several feet. But the military cares a lot about several feet. If they're going to get a smart, bomb into some spider hole underground somewhere, they want to hit that accurately. So how do they do that? So if they were off by just a foot or two, they would not be able to hit their target, literally. And so we know now by measuring how fast light travels, by bouncing it off things in the solar system, that not only does light travel at this constant speed that we know is 186,000 miles per second, or 300,000 kilometers a second, but all forms of light, including the heat that I study, microwave heat, that travels at the speed of light. So we actually have measured that across the solar system, across the galaxy, and beyond that, we just haven't lived long enough to be able to measure things beyond our solar system, shall we say. So we in order to know more about the constancy of nature of these effects, we would have to test it even more precisely. But the point I'm trying to make is that if you can test something, so let's say light travels 186,000 miles per second. There's 5,280 feet in a mile. So you could, if you're off by 1 foot, you're off by 5,280th out of 186,000 miles. So you can test it to incredibly high number of decimal places. You'll never be able to get it perfect. But it's the most perfectly tested theory that we have. So it's a model. When I say the theory of relativity, it's a model for the way that light behaves, not only how light behaves, but how gravity affects light's travel. And it's the most accurately tested branch of nature that we have. So in no way do I mean disparagingly when I say something's a theory. You could say that the Pythagorean theory is a theory, but it's perfect in that you can prove it mathematically. You can prove that 1 + 1 = 2, and you can prove that. That's a theory. It's part of what's called number theory. That proof could be 3 times thicker than my book, which is already pretty hefty, like 296 pages or whatever it is. So if you imagine something that you want to confirm as what's called epistemology, how do you know something as a fact? How do you know something? You confirm that what your idea of something actually agrees with the way that you observe the world. We're trying to observe. I always say we're trying to the island of knowledge that we have is big. But the ocean of ignorance, as John Archibald Wheeler used to say, there's a coastline that defines the boundary between the island of knowledge and the ocean of ignorance. Our job as scientists make the boundary, the coastline, bigger and bigger every day because and the coastline, it kind of represents this meta state where we don't really know. We kind of know that we don't know something. Yeah. But the ocean is infinite, and that's what's so exciting about doing science. It's like you're never bored. You never get bored of what you do as a scientist.
So I feel kind of like an expert because I saw Interstellar.
Yeah.
But just checking in with you, is that
so funny that you bring that up?
Possible that because what they're saying really if we travel a certain speed, right, and go a certain place, that time could be moving much faster in one place than another, right?
Yes.
Right. That's sort of what it's...
Yeah, so I have a funny story about that. So I travel a lot internationally, and a couple of years ago I wanted to get one of these global entry cards, and to get it you have to go down to the border, you go down to Chula Vista or whatever, South San Diego, you go to the Customs and Border Patrol, and you check in there. And they're going to ask you, why do you need this and whatever. There's a guy right in front of me, and I heard them asking questions. I was pretending to listen on my phone or whatever, and I heard what they were asking me. I was like, what do you do for a living, sir? And he's like, I'm a scientist. I'm pissed because how many they're gonna think we're like drug mules and we get communicating this together. He's like, I'm a scientist. I think it's like an oceanographer or something like that. They let him go. Okay, have a good day, sir. They come to me. What do you do? I'm a scientist. Oh yeah, what do you do? And I'm like, I'm an astrophysicist. And they're like, oh yeah, what'd you think of Interstellar? I haven't seen it. And by the way,
litmus test.
Still haven't seen it, which really pisses me off. I still haven't seen it. It's published by my same publisher, the book that describes the physics behind it. And the consultant to it just won the Nobel Prize, Kip Thorne up at Caltech.
Oh, did he steal your prize?
No, he didn't steal my prize. I have an interesting story about him later on. But so this guy's like, well, what'd you think of Interstellar? And I could BS with the best of them. So I was like, well, the interstellar warp drive that they're trying to communicate means time dilate. And the guy's like, okay, you think you're smarter than me? You're right. And I was like, well, you guys got the guns. You guys look pretty nasty. I better be nice to you. So they ended up giving me the card. So getting back to Interstellar, it is true, and it has been extremely well tested. There are particles. It is true that things moving at a high speed create there's what's called time dilation, when you can prolong a lifespan of something if it's moving at high velocities with respect to something else. But you ever been sitting on a train or in traffic, everyone else starts moving, and you feel like you're moving and they're staying stationary? So ask yourselves, your listeners should think to themselves, what does it mean? What does motion mean? How can something in motion experience some physical phenomenon when the thing that you're calling stationary, maybe that's moving? So that's a paradox. That's something that's related to what Einstein used to think about, called the twin paradox. Imagine two twins, and my wife and I just had twins. So if I imagine the girl and she stays at home, and I send my son off near the speed of light, and he goes out to Alpha Centauri, 4 light years away, and then he comes back to Earth, he'll actually be about the same age as he is now. He won't have aged at all. She could be, 100 years old by the time he comes back, depending on how the relativity of time took place for him, what speed he specifically went out at. That is the
Sorry about
that's
that.
okay. That is the determining factor. Now, what is the difference between their two motions? I asked
One's
you.
going very fast.
Well, one is going really fast, but just like you sitting in the train station, I mean, how do you know that you're moving? Velocity
Just relative.
is relative. So that's where relativity comes from.
Relative to what? To us spinning on this globe?
So it could be just a twin sitting here. So she could be in space, no globe, nothing around. She could just be sitting in space. He goes off to Alpha Centauri at this half the speed of light, comes back at the half the speed of light. What's the difference between those two? Couldn't he just see her moving away from him? And it looks like he feels like he's stationary, and that's why he doesn't feel like he's aged at all. And then she comes back, and he's 100 years older. What is the difference between those two is that he had to make what's called acceleration. He had to change, I kind of snuck a fast one by. He had to change his velocity, which is a phenomenon called acceleration. When you change the velocity, like your accelerator in your car, you change your velocity. He did acceleration, she didn't, because he turned around. And all the aging that she experienced, according to his clock and his watch, took place when he made that U-turn and came back. That's what relativity shows. So things in motion that are truly in motion, yeah, it's truly mind-blowing. When they're in motion, their clocks run slower. So there are particles called muons that exist. They're kind of like electrons, except they're about 100 times heavier, I think, something like that. And they enter the Earth's atmosphere. And when I have a bottle of muons in my lab, eventually they'll decay into other particles, including particles of energy called light and photons. In my lab, they last for, say, half a second or less, actually half a millisecond, I think. But when they crash into the atmosphere, they're accelerating and they're decelerating. Their clocks will run a little bit slower. So we can measure the lifetime of those objects, and they actually live longer than the ones in the laboratory. So we've tested this time dilation, this relativity, the twin paradox, using twin muons, not twin people. That would be kind of cruel. And you also can't accelerate something big like a human being to near the speed of light, whereas you can with a tiny little particle.
So you're saying that every time I get in the car and drive to LA, I'm actually at a very, very small bit staying a little younger. Because I feel like I'm dying.
That's right.
I feel like I'm dying.
That's right.
Very slow death.
Didn't we actually put an atomic clock on airplanes and run around? Okay, go for it. You'll do better service than I will.
Yeah. So what they did is they took clocks that are the most precisely precisely automated clocks that exist, called atomic clocks, that count the number of oscillations of a certain isotope of cesium, and they measured how many pulses of a clock, which is all a clock is. Your heart's a clock, the ticking of a pendulum's a clock, the sun going around. Anything that's periodic can be a clock. They measured how fast the cesium atom was ticking, and they found that when you flew two clocks around the world in opposite directions, they would agree that they had experienced less time than a stationary, identically otherwise clock on the Earth's surface.
By
this is like maybe even a second or something like that.
And that's just at a regular airplane speed.
That's
600 miles an hour.
Yeah, fraction of the speed of light, tiny percentage of the speed of light, exactly by the amount that Einstein's relativity. So twice that, because there's two planes moving in opposite directions with respect to each other.
So is it possible that we could move half the speed of light without dying?
So I think the fastest we've ever done anything in terms of spacecraft that ever left the solar system, we can travel. So I know we travel basically, it equates to about a light hour per year. So you're talking about really, really tiny fractions of the speed of light. So if you convert a light hour, it's a measure of distance. How far does light travel in an hour? And then you take a year and you convert everything to seconds. You're talking about like maybe a couple hundred kilometers per a couple thousand kilometers per hour for something like on the Earth, and then in space maybe 10 times that. I mean, we got to the moon, which is 1 light second away. It took about a week. But even if it took a day, I mean, you're talking just tiny, tiny fractions of the speed of light.
So even if we could figure out, let's call it, say we could figure out how to travel at the speed of light.
Yeah.
Isn't things so far away, like a star that we're looking at, would it still take
it would take 4 years. It would take 4 years to get there if you're traveling at the speed of light. The issue is that to accelerate something at the speed of light, the mathematics works out that you have to give it energy at an increasingly geometrically progressing rate, such that the amount of energy to accelerate even the tiny little flea to the speed of light would be infinite. So you can't actually get
a lot of gasoline.
Yeah, so you need a lot of vibranium. You need the vibranium. We're working on it in the lab. But if you actually could do something at half the speed of light, so it would take twice as long. But even that is what I'm saying is we're at maybe 1% of the speed of light right now with our best technology. There are plans to accelerate a cell phone camera not a cell phone itself, but like the size of a sensor of a cell phone, a 1 square centimeter size cloud of cameras, shoot them like tiny little sails using laser beams. Pew, pew, everybody loves laser.
Are you making shit up right now?
No, this is a project funded
Mike
by
Myers movie.
Let me make it even
Laser
worse.
beams.
Laser beams.
Laser beams.
It is funded by a Russian billionaire. Does that not
wow.
intrigue you even more?
Right.
So there's this Russian guy named Yuri Milner, and he created this project, $50 million project, to shoot these tiny, and that won't even be like pennies on the dollar of what it actually takes, to accelerate these cloud of sensors to the nearest stellar system, which is called Proxima Centauri.
Okay, wait, hold on. Rewind.
Yeah.
Where's Proxima Centauri? What is that?
So it's about in that direction, and it's about 4 light years away from us. So light travels about, as I said, 186,000 miles per second. It will still take 4 years for a laser beam to get there. If we shot just the laser beam.
That's at the speed of light.
That's at the speed of light. Now, what people say is that you could use a sail in space that has no wind resistance. So there's no air friction. There's nothing in space. A sail.
An actual sail.
Yeah,
like we used to sail.
it's called a light sail. Yep. And so if you blast something with light, it has energy, and that light can give it a kick. And if you shot it with a big enough laser and you didn't disintegrate it, and it was able to capture that energy, it could accelerate without any friction. So it could actually go very comparable
faster
to
than the speed of light?
No, it can't go faster than the speed of light because it's made of matter. So this is like an actual chip from your iPhone or something even smaller with a little antenna on it, because it's no good if it goes there and doesn't take any pictures and send them back.
Sure.
So this is a very advanced project. I don't know if it'll ever be successful. It's the first time that people have thought that it's actually possible to do it, though, which is kind of an interesting time in human existence. We've known how big the universe is and how small a little, one of the scientist Jill Tarter, who is the inspiration for Jodie Foster's character in the movie Contact, she's a real person. She describes like how much of the universe have we explored listening for other civilizations, listening for ET. It's equivalent to like a thimble of water in the Pacific Ocean. It's just minute how much, because we've only had the technology to do it for a few years, maybe a couple, maybe 5 decades, 6 decades. So not only are we just learning potentially about civilizations that are at most, 70 years away from us by the speed of light travel, they're also only learning about us, our existence. We've only beamed radio waves off for 70, 80 years now, that they could be aware that, there was an Olympics in 1936 where Jesse Owens was, right? So that's in the movie too. So
hold on real quick, because I'm intrigued by this.
Yeah.
This other universe that we're talking about, that could be how many years away?
Oh, so this is another solar system.
Another solar system.
Solar system. That's 4 years at the speed of light.
And we photographed that?
We know that the star is there. We know how far away the star is. We know accurately.
When you say the star, what do you mean?
So there's a star.
One star?
Yeah, there's a star like our sun is a star.
Okay.
Around the star could be a planet. We think there are planets around it.
But we can't see far enough.
We can see the effects of the planets on the gravitational field of this star. So it's a complicated chain of reasoning. Scientists think there are planets there. There's a reason to suspect that there could be a planet there. It might have no life on it. It might be completely unlike our solar system.
There could be 100 planets there. We have no idea.
It could be 100 planets. It could be 1,000 planets. It could be none. But the thing that's interesting about it, it happens to be the closest star to our sun. So there's no other star that we could get to. And this project could take I think the baseline is 25 years. So they're talking about traveling at, maybe 15% the speed of light, 20% the speed of light. So that means it will take 5 times longer than humans. So it would take 25 years to go 5 light years. 25 years to go 5 light years distance. So it's still very ambitious, probably not going to be successful, may not happen in the time scale. But my excitement about it is based on the fact that it's the first time that, at least on paper, it pencils out to be maybe practical. I mean, it's not as fanciful as it would have seemed 100 years ago. I mean, don't forget, we've only been flying airplanes for 114 years or something like that.
Yeah.
And to think that we've gone to this point where we've been to other solar systems, we've been to other planets in our solar system. We haven't yet left our solar system, but we have sent objects that have left our solar system. And so now they're in this no man's land between our solar system and this other solar system that I'm describing, or possible solar system.
They're supposed to come back, right?
They're not going to come back. They're going to send back radio waves, this thing that they're shooting out, that they're shooting back. These little cell phones will have little antennae on them. They'll broadcast, hey, we're here. Here's a picture. Here's a selfie of me, the satellite, the little tiny chips. They're going to send out like 1 million of these cell phone cameras because they'll be really cheap in 25 years. And they'll have the resolution, they'll have the imaging, and then they'll have enough energy from the star that they're near, but they'll keep going right past it. There's nothing to slow them down. So they'll just here's Proxima Centauri, wave as they pass by, and they'll send light beams back to Earth. And if you have a million of these things, the thought is that at least a couple of them will be facing the right direction towards Proxima Centauri. They'll have the right geometry to send back to the Earth, and it will have enough energy. Yeah, and it'll have enough energy to lay dormant for 25 years. This thing, imagine like switching on your iPhone in 25 years. Do you think it would power up? I mean, they have to have enough energy from the star, solar energy capture. And by the way,
how quick does the radio waves?
The radio waves, they all travel at the speed of light. So actually, as soon as they get there, let's say they got there tomorrow, we wouldn't know that they got there for 4 years. Because they're 4 light years away, 4 radio wave years away, 4 microwave years away, infrared years, all the same. A light of all different colors, literally, travels at the exact same speed.
So the closest star is 4 light years away.
Yeah.
And that's within our galaxy.
That's in our galaxy.
And how big is our galaxy?
Our galaxy is enormous. So our galaxy is about 100,000 light years across.
Okay.
And we're about 2/3 of the way out. So we're about 60,000 light years from the center of our galaxy.
How do you even measure that, though? How do you even measure 100,000 light years? Like, will you draw it on a map?
Yeah, exactly.
I mean, what are we just taking pictures from telescopes, right?
So we're using telescopes. We're using geometry, which is extremely well understood, and we use something else, which is actually described in some detail in the book. That nature is kind to us. It's not malicious. It tells us things about itself if we're clever enough to decipher what it's telling us. So it's like the movie Arrival. I don't know if you ever saw it. Yeah. Like if you can actually interpret what there's a contact or. If we can interpret what nature's the guideposts, the rulers, the clocks that nature gives us, we can learn a lot about it. But it requires us to be lucky, and very clever, and very hardworking. So it turns out that you can actually measure how far away something is using a ruler, more than just like laying the ruler out and measuring on the ground. You can use something called trigonometry, geometry, and things like that. So one way you can do this, you guys can do it right now. So pick some part in the room. I'm going to cover up like the door handle and close your eyes. Close one of your eyes, hold your thumb over, cover something up. Now open the other eye and close the eye that you're on. It shifts, right? It's shifted back and forth. That's called parallax, that changing of the angle. What it was based on, if you guys had really wide set, I have really narrow eyes together because I look in telescopes all the time, but if you guys had like really wide set eyes, the angle would be much bigger, right? Because one eye would be looking at a really radical angle compared to the original eye that you're looking at. So when something's separated by a large amount, you can actually measure very big angles, or you can measure very small angles very accurately. How do we do that on Earth? Well, the Earth is kind of like the diameter of the Earth's orbit is like the separation between our two eyes. So today's in July. If we measure the position of a star or a planet or something close by to us against the background of really far away galaxies and stars that we know to be much farther away than our own galaxy or very distant within our own galaxy, then you wait 6 more months later, you're across the orbit. So that's like your other eye now. Now you're in January. Measure that same star. You've seen that it would move. It would move by much, much less than a degree. It turns out it'll move by fractions of a thousandth of a degree. That change in angle, combined with the knowledge of how big the Earth's orbit is, 93 million mile diameter, we know exactly how far away that star is. The farther away,
it's like triangulation, right?
It's triangulation. It's exactly where it comes from. So that process allows us to measure things in our own galaxy. Now, once you get things in our own galaxy, you could be lucky, as we were in the 1900s. I say we, but astronomy was lucky. Astronomer named Leavitt, Henrietta Leavitt, she discovered that there was a type of a star that would blink on and off every couple of days. And its blinking was related to how much energy it was putting out. And she could measure the energy by how bright the star was. And she measured over time, it was like breathing. It was getting brighter and brighter, then it was getting darker and darker. Brighter and brighter, and it never stopped repeating. So it was like a clock. And she realized that she could use the properties of that star and how bright it got. She could use it like a light bulb at a distance. So not only can you do this thing with your eyes, but you ever see like a car, a light from at a really great distance, as it gets half as far away from you, its brightness goes up by a factor of 4. So that means you can use the brightness of something as a ruler too. So she realized she could use these special stars called.
What do you think that was?
She was using this type of star whose intensity changes periodically and it never changes. It's like a clock.
She's like gas moving in and out.
It was gas. It was the size of the atmosphere of the star getting bigger and smaller, kind of like sunspots. But it was the way that this star's dynamics work. Not all stars are like this. Most stars have some degree of variability. This star would change its brightness by a factor of 2. So it was either getting closer by a significant amount, which didn't seem likely, right? How could it keep moving back and forth a good fraction of the Earth's distance? light years we're talking about, in a couple of days. That's not possible. So she realized that it was actually because the brightness was changing and she could measure the brightness precisely. Therefore, she got its distance, called the luminosity distance to the star. When she combined that, she also had a measurement of its parallax. So parallax goes back to the ancient Greeks. They realized you could measure things with angles, like a surveyor scope. That goes back to, to the ancient Greeks. Archimedes and people like that. She realized she could she could combine something that she knew, which is the geometric distance, the parallax distance, with the luminosity distance, which she didn't know. And she did something called calibration. When you measure something, compare it to something you understand perfectly, you can then calibrate the new thing. And then the new thing, she could stretch out to other galaxies have these same stars in them, called Cepheid variable stars. And in fact, on Mount Wilson in 1923, Edwin Hubble, the progenitor, the father of much of modern astronomy, and the namesake of the Hubble Space Telescope, he discovered there was one of these Cepheids blinking on and off in the Andromeda Galaxy. And so he realized that galaxy is actually 1 million light years away from us. So that galaxy, and it kind of looks like the way our galaxy looks. So they start to get a picture of what our galaxy looked like. And then from the geometry of where these other objects were in that galaxy, he measured how big that galaxy is. And he could infer from other Cepheids in our galaxy how far across our galaxy stretched. And I'm skipping hundreds of, of examples and astronomers and contributions along the way. I kind of give a condensed history in the book because along the way, there's a substance in the universe called dust. And it's kind of like the dust, like that you guys are familiar with. Yeah, you got truck dust.
Black. Don't get a black car. Every time I buy a car, I say, I'm not going to get a black car. And then I just end up, that looks so good.
I got a dirt-colored car.
Yeah.
Just go with quicksand.
Yeah, dust looks good on dirt.
That's right. Yeah, dust and rust. So, and with kids, we learn a lot about dust, right? So you guys don't know about it, but Patrick and I know about it.
Dust, like angel dust? What are you talking
about? Hopefully not that. So in the universe, stars don't live forever. Just like in Hollywood. The stars go out, they go out with a bang. The brighter they burn, the quicker they burn out. That's right. No,
our star's on its way out too.
Yeah. So when a star dies, it does so, depending on how big it is, it can do so in spectacular fashion. And it can blow apart all the things that it was made of into space that surrounds it. And some of those materials are really lucky for us that were blasted out into space because they form the material in our planet. Like, there's not some machine in space that churned out a planet. That material that's in our Earth had to come from somewhere. And if you ever think about where did it come from, there aren't that many sources. There's no 7-Eleven in space. You can get everything, right? Home Depot, Planet Depot. Instead, when a star that existed before our sun, 5 billion years ago perhaps, it exploded. It shot out meteorites and things like material, metal, dirt, rocks, dust, and things like that. Eventually that formed.
Through gravity?
Through gravity, exactly, yeah. So it just attracted it to it and got bloated up and made a disk.
Bigger, more gravity,
Exactly. And that ended up creating our entire solar system. And parts of our solar system that didn't form into planets are what we call meteorites, asteroids, and things like that weren't big enough to form a planet, are still pretty big, but aren't quite big enough. But they're basically giant rocks of dust. But there's also smaller pieces of dust that are in the solar system. And those smaller pieces of dust can absorb light from stars. Depending on their size, they can trick astronomers like this woman, Henrietta Leavitt, and Hubble himself. They can trick you because if you saw let's say I told you, here are two light bulbs, one is half as bright as the other one. So you say, well, that one must be 4 times farther away. Or, actually, it's 4 times less bright, a quarter as bright. It must be twice as far away as the other one. But if you knew all of a sudden there's dust, like an inch of dust covering up the first one, it could actually be at the exact same distance. Mm-hmm. So dust can deceive you into thinking something's farther away and bigger than it actually is. And for a long time, Scott, you asked about, well, how do we know it's really big? They thought the universe they thought our galaxy was the entire universe. So there's about 100 billion stars in our galaxy, and we've known that for quite a while in our galaxy. Now we know there's about 100 billion galaxies in the universe as well. But for a long time, we didn't know.
Hold on. So it goes galaxy.
Solar system is where our
sun is.
Solar
system is where we're at.
Yep.
Okay. There's multiple solar systems.
Many, could be billions, trillions of solar systems.
We have no idea.
Yep. Mm-hmm. Planets within
But if we don't know how many solar systems there are.
Yeah.
How do we know how many stars are in
Well,
our
so
galaxy?
we can count the number of stars pretty accurately. Stars are actually pretty easy to see. They clamor for attention. Again, a lot of parallels in Hollywood. I'm not going to mention any names, but yeah. They're bright. They give a tremendous amount of energy. There's like the equivalent of 1 million Hiroshima bombs going off every second on the sun's surface. Incredible amounts of energy. Pretty easy to detect, even if they're really far, literally across our galaxy. So all you do is you count up, well, how many stars do you see in the distribution of them on the sky? And you don't have to count up each one. You can count up, make an average. Just like if you're trying to estimate how many people are at Petco Park on a Padres game, you can estimate it. You're not going to get it perfectly down to the person. You can count each person. That would be very tiny.
We don't care about sports here. Let's find out. Right? San Diego.
San Diego, I know. I always say that the easiest job in the world is San Diego weather forecaster, and the hardest part is San Diego sportscaster.
Right.
It's like the worst job in the world. Anyway, so we estimate, exactly. And not only can you estimate how many stars are in our galaxy, you can estimate how many galaxies there are in the universe. If there is just one universe, the question we're trying to answer with our telescopes nowadays is our universe alone? Do we exhibit the same kind of extrapolation that you were making, or you said, we know there's lots of stars, lots of planets, lots of solar systems, lots of galaxies. Well, who says there's not lots of universes? For a long time, we thought we were the center of the solar system. We thought the sun went around the Earth, right? Mm-hmm. I described that in the book. That also came about, through a variety of different features and forces. Most people think scientists are really kind of dispassionate. Robots are just we just walk and we're like Wikipedia, just walking around, right? But in reality, science is a human endeavor. Like you guys have interviewed plenty of scientists on your show. You know this, that scientists are just normal people, but they happen to do abnormal things with their time. And one of those things is to do really accurate studies of things that could be complete minutia to other people, but to us it's really fascinating. But we're not immune from the forces that just an ordinary average person is interested in. So we sometimes have preconceived notions about the way the universe should or should not work. So for a long time people thought, well, the sun seems like it goes around the Earth. And in fact, I challenge, I bet you could ask 100 out of 100 people on the street today, unless you get away from a university campus, and say, prove to me that the Earth, isn't the center of the solar system. Most people couldn't do it. I won't ask you guys to do it. And then you could even ask them, prove to me that the Earth isn't flat. I love that. You're like, all these people make fun of, this flat Earth guy. Yeah, I mean, guy's probably pretty much, a fool. But in reality, it sure does look pretty flat. Like you guys got down here, you didn't use a globe to get you didn't use your sea captain hat.
Guarantee
and a buoy,
you,
right?
You interviewed 100 people, they wouldn't be able to explain to you how it's not.
Yeah.
Right. Well, because people know it's not.
Right.
Yeah.
You'd be like,
So I was indoctrinated as such.
Exactly. So how do you get past the indoctrination? How do you get past this notion of, well, of course, it's obvious. And in fact, it's obvious to really smart people. And like, it kind of forgives you. Remember that, A Few Good Men, like when Jack Nicholson's saying, like, well, you want me on that wall, you need me on that wall. My theory is that, like, the average person who's not a scientist wants there to be people that are smarter than him or her about science, at least, so that they can not think about it themselves. Like, it kind of absolves you a little bit if you say, well, that person won a Nobel Prize, she or he can tell me what to think about blah, 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 and you can fill in the blank. And sometimes you get this what's called authority bias, or where you respect this person because he's really smart. Like Albert Einstein had a lot of like really crazy notions about like communism and all sorts of stuff, but people took him very seriously. He thought there should be no borders. I mean, maybe I don't know what your politics is, but a lot of people considered it like, wow, it's really brilliant. Like we should just lay down all of our arms and have no
humans.
nations and and everyone's gonna love each other. And like, it didn't work in Europe, like didn't pan out so well. But because he was so brilliant in physics, he obtained this kind of aura about him that led to what's called authority bias. So in science today, that's the Nobel Prize. And he also won a Nobel Prize, but not until much later in his life. But the point being that scientists are susceptible to biases, and one of those biases, confirmation bias. You want to prove that what you thought. What's that?
Your theory, right?
Yeah, you want to prove your theory, and it could be for a variety of practical reasons. You need a job. You need to keep, the
lights on.
Yeah, you need to keep the lights on. You need to keep the telescope, oiled up. But no, we don't oil telescopes. That sounds perverse. But in reality, what dust did to astronomers throughout history, and including my experiment, which ultimately caused us to lose the Nobel Prize, was it tricked us into seeing something that wasn't actually there. We saw what we wanted to see, and in part that was driven by these human emotions, and that's why I think it's interesting to people when they read it. They're like, "Oh well, I didn't realize it would be a memoir because it really is a memoir. It's more of a kind of an autobiographical sketch. It has science in it to explain all these things that we've been talking about, astronomical topics. And then, kind of this discourse on whether or not these, should we have Academy Awards for scientists, basically. And that's kind of been the ultimate introspective moment for me in realizing what did it do to me, because I'll tell you honestly, I wanted to win a Nobel Prize at all costs.
Sure.
I was one of those actors, sounds like you're not like that, who just wanted to win an Oscar. I'm going to prove to people, and in my case with my father, who was a pretty eminent scientist, and I wanted to prove to him I was better than him or I was as good as him, and he should,
it seems much more important to have awards for scientists than it does for actors.
Yeah. I mean, I would agree with that, but the process by which we award these. So, for example, my wife was an actress for a long time. Every year she's in the SAG, so she gets these DVDs. Sure. You probably get them, right? So it doesn't only say so and so Scott Eastwood nominated for 10 or won 6 Academy Awards for Best Actor, but it says how many times you were nominated, and not only for an Academy. It'll be Palme d'Or and the Sundance this and this and that. It will say every single thing, not only that you won, but you were nominated for. And I think that's very interesting. If I told you that the Nobel Prize, you'll never know. If I didn't write this book, no one would ever know that I not only was nominated for a Nobel Prize, but I was actually a nominator. I was like the Academy itself. I was nominating people to win the Nobel Prize the year after I lost it. So imagine you get asked to nominate, you lose the Oscar, you're sure you're going to get it for Fast Furious 5 or whatever you're in, and then you don't get it. But then you're asked the next year, who should get it? Who's a better actor than you, Scott? Tell me about, in that case, that's what scientists... Yes, it was humiliating. It was embarrassing. After we had retracted it and basically, shown that we didn't make a blunder, we didn't plagiarize, we didn't, fudge our data, we had made a mistake of confirmation bias. And admitting those mistakes, after being on the front page of the New York Times and having millions of views on our YouTube video of the discovery, and all the scientists being celebrated as going to win the Nobel Prize, to have to retract that. That's sort of what the book is about. And how do you deal with not winning, losing the Oscars? You might not win an Oscar. How do you deal with that? Now, for you, it sounds like you have equanimity about it. Fine, that's great. And I wish I had that in an earlier time in my life. But for scientists, we get told things like you got to get a Nobel Prize or be on the trail of a Nobel Prize to get tenure or to get funding. And when you do get funding, just like an actor, when they win an Oscar, your dad can do whatever he wants, right? And he can pick and choose. The point being that it has an outsized influence conferring the authority bias. The question is, what does that do next? How does that affect a young person who's coming up, who doesn't know exactly that she has the right stuff to win a Nobel Prize or not? And I agree with you 100%. And that is the conclusion. We should do it, actually without regard for those accolades, because that's the purity of the craft of being a scientist, that you get to paid a decent amount, not tremendous amount. But I make the case in the book, in contrast, that, the Nobel Prize might be having a negative effect on science, as opposed to what Alfred Nobel wanted.
Well, it's such an important notion, just even in today in society, what's going on. It's I believe that global warming is not real, so I'm going to go find information to make that
right, to confirm
the case.
Your hypothesis, right?
Yeah.
Mm-hmm. Right. And what is that doing? So my theory is if science is undermined, if they doubt the scientific method, which is basically, cause and effect, reality, you're actually asking what is the effect of a scientific process on something that we humans can observe, the cultivation of new knowledge. Imagine if you lived, it's almost impossible for us to imagine if we lived in a universe where cause didn't precede effect. And truth could be completely variable, not just the twin paradox, not just relativity, but there was no scientific epistemology. You couldn't actually determine a fact. Okay, well, that won't happen, but science is the bedrock by which we discover new laws and new facts and new truths about how the world works, and it's predicated on logic. So once scientists become, I don't want to say corrupt, but once we never get ethical training and basically, very rarely do we get ethical training. How do you behave when you have this huge discovery that everyone wants you to make and you're going to win a Nobel Prize if you do it? But you have these lingering doubts that a lot of us expressed before this happened. It was like a steam train. You couldn't stop it. There was so much momentum and so much pressure to do it because billions of dollars are at stake for these types of science projects. You wouldn't think it would be the case, but it is.
and you want to make those people happy, and there's a lot on the line.
Absolutely, 100%. Yeah. So there's a lot of pressures, and you know, it affects people's and affects how the soul of science is really going to be treated in the modern world. And I want science to thrive. I think it's the most, you know, it's the most important thing that society has. And most of the time it's apolitical. I mean, I mentioned global warming. Forget about that. And forget about evolution for a second. I mean, I believe in evolution, you know, as much as I believe in relativity, which is, you know, 100%. But on the other hand, you know, if you're dealing with nuances and new discoveries and things that no one has ever really, you know, gotten to before, if you undermine that and the integrity of how science itself is supposed to be conducted, I think society is at risk. So it's kind of like a warning cry, you know, and I think the Nobel Prize is kind of an emblem of it. So one of the Nobel Prizes is a Nobel Prize in literature. And this year it's been canceled. So the King of Sweden was involved in its cancellation because one of the people that was the director of it, her husband was cheating on her and like having sex and doing all sorts of bad stuff with women that wanted to win the Nobel Prize in literature, trying to curry favor with him. But then she got fired for what her husband did. And so like, well, maybe she was a part of it. Maybe, who knows? But now what's happened is that the integrity of the Nobel Prize has been questioned in literature. People have called upon it to be canceled before. It's been given out to people like terrorists have won the Peace Prize. People that create more armies in the world have won it. And in the case of the Physics Prize, I'm worried that's going to happen. So part of it's kind of like a cri de coeur to, you know, kind of prevent the Nobel Prize in physics, which is my beloved prize, from ever going away.
Interesting. What are you working on now?
So now I'm working on raising 5 kids, and I'm working on a project that has benefited from the lessons learned of this project called BICEP. So BICEP is a small telescope at the South Pole. From that telescope, we've learned a tremendous amount. Not as I said before, the results are correct. The interpretation was wrong. We said we saw the spark that ignited the Big Bang, as I discussed in the beginning of the show. The actual thing that we saw was dust. We saw the most humble, boring schmutz in the universe that actually tricked us into seeing exactly what we wanted to see, both scientifically at heart, but also to win the Nobel Prize. That was definitely an inescapable part of it for some of us on the team. From that project, we've now learned how to correct those flaws, biases, those preconceived, you know, notions that we had about how the universe, quote unquote, should be. From that, we've designed a new experiment called the Simons Observatory, and that's located in Chile. Instead of the South Pole, it's located at about 17,000 feet above sea level in the northern Atacama Desert of Chile, which looks a lot like, I mean, it could be in The Martian Part 2 or whatever. It looks just like the surface of Mars. It's got active volcanoes nearby. It's got craters, salt flats. It's got geysers. It's an amazing place to work and to live. And we want to get above as much of the Earth's atmosphere as possible. So that's why we go to the South Pole. The South Pole is about 10,000 feet above sea level, effectively. The Atacama Desert, 17,000 feet. So you're above almost half the atmosphere when you go to the site in Chile. And when you look up, it's like the sky is black. It's not blue, it's like black right above you. So we've learned from what BICEP did wrong. We're trying to correct that for this new experiment called the Simons Observatory. And one of the things that we're doing, whereas before with BICEP, you could make the argument maybe I would have won the Nobel Prize, maybe one of the other founders of the experiment or co-leaders of the... Now, so there were only a handful of people, so only 3 people can win a Nobel Prize according to these made-up rules by the committee in Sweden. Now we've got 245 people working on the experiment. And it's not that that's never happened before, where a lot of people were required to make a scientific discovery that resulted in a Nobel Prize. But now we're basically like, not F you to the Nobel Prize, but we just don't care about it. It's no longer the animating impulse that it once was. Because I think for me especially, look, you know, I don't know if you ever, how biblical you've ever gotten in your life. I don't mean, you know, in the negative sense of the Bible, but I always remember reading about the golden calf. There's a famous story of the golden calf where the Israelites got out of Egypt and they had all these plagues and they killed all the Egyptians. God killed and then 40 days later they go into the desert and then Moses disappears for 40 nights and he's not there. And the Israelites make a golden calf out of gold and say, this is our God. We're no longer going to worship this Yahweh guy. We're going to worship this calf that we made ourselves. And I used to think that's so stupid. Like, how can any I'm Jewish, so I'm going to appeal to my Jewish egotism, but say, like, I thought Jews are supposed to be smart. You know, like, how are they worshiping this stupid piece of metal that they themselves made? And it just didn't sound true to me. And I was like, maybe the whole Bible just doesn't make sense. It's not worth reading. But in the end, I remember just the day that I submitted the manuscript for this book, a guy who won the Nobel Prize. He came to UCSD to give a talk, and he brought his Nobel Prize with him. He brought the actual golden chunk of metal. It's like 24-karat gold. It's like a pound, and everyone was like oohing and eyeing. All these physicists were oohing and eyeing over it. And they were just like worshiping it. And they were worshiping him. They were like posing for selfies with him, kissing it. Nobody bowed down to it like the golden cap. It came pretty close. And then even I, who had written this book, like I was like, can I take a selfie with it? You know, like it just showed me that within human nature, it's natural to want to idolize people and idolize things. And when you can do, you might expect that. I mean, we talk about American Idol, right? I mean, in Hollywood, in that world.
What do you think that is in our psyche that's...
I think it's related to this authority and status bias. Like, why do you think Kim Kardashian will go to the White House and talk about prison reform? I mean, it's like, has she studied papers and done literature, social criminology? No, she's just like, someone who's got a lot of fame and attention. I think it goes back to the hunter-gatherer tribes. Like, if you were a guy, especially back then, now it's more egalitarian, but the more you knew, the more past history you knew about, like where to hunt, or don't drink that pool over there, don't eat that mushroom, eat that one.
You were like the badass.
Yeah,
you were the dude.
Exactly. So you had the authority, and you probably got more women, and you probably had more procreation. And so, the more powerful that was, I think that ties into it. And because we are not gods, our task is to become, and we shouldn't try to supplant, the actual God, if that's something you believe in. But it's natural because you want heroes to worship. I mean, sports teams, like I went to the Padres game yesterday, and kids are worshiping, all these hitters, or whatever, not on the Padres, but on the Pirates. But nevertheless, they do have it. And even my daughter, my middle daughter, she has a poster not of a sports team, not of Miley Cyrus, not of she has a poster of the last woman to win the Nobel Prize in physics.
That's a great mentor that she worships. That's
right.
Great. How do we get young kids?
And that's not divisive either.
Right, exactly.
No, but I mean, how do we get more young people to have those people they worship?
That's right. No, so that's a big thing that we think about, especially with the kind of searching for, because I think there's a beauty in the simplicity of, we were talking before we started recording, just about minimalism and kind of record. That's what science is. Science is about kind of paring away all the false red herrings and everything else and getting what is the core of truth. And science, the word science in the language Greek, it means knowledge, but it doesn't mean wisdom. Like wisdom is a different word. I don't know what the word for wisdom is in Greek. I should probably learn it. But it's true that knowledge is more than just the accumulation of facts. When you have that knowledge plus accumulated wisdom, you can have wisdom and true insights into the way nature works. And I think if we can cultivate a reverence for that, then you might see people. I mean, right now it's, the culture is a lot more obsessed with sports stars and music stars, and I don't think there's going to be a, Nobel Prize idol on TV anytime soon. But I think, in the past it's been done by, we're fighting some enemy, the Soviet Union or China or whatever. I hope it doesn't have to be like that. I hope we can pursue knowledge for its own sake, but knowing past history, maybe that's not going to happen. Maybe we're going to have to wait for the asteroid to come to Earth in 50 years and, then train a whole bunch of people to deflect it away and figure out how to save humanity. Or just call in Ben Affleck and Bruce Willis.
Call them in. I think I've always been more enamored by scientists, more enamored by people who were, and maybe it's because I grew up in a family that, my father is who he is, and I just realized people are people. They're not these mythical.
That's right.
People. I was always fascinated on merit, right?
Mm-hmm.
On people who go out and do something, people who, like yourself, or trying to discover something, trying to benefit society. Not to say that, certain people aren't, I guess, but it's, I guess, I don't know, the way I always measured it was through some sort of, I guess maybe I was more fascinated with academia a little bit, just
something tangible that's contributing to growth of humanity rather than entertainment, maybe.
Yeah, and look, we all need entertainment as well, but I think there should be a balance, right? I mean, if you are only focused on entertainment, then are you putting forth something that's going to, benefit some?
I remember the documentary filmmaker Ken Burns, who's probably the dean of all documentary filmmakers in America today. He spoke at my college graduation at Case Western, and he said something to the effect of, a lot of us were science majors, and he's like, science is phenomenal at discovering new things and providing technology and defending civilization, whatever that means, discovering cures for stuff, discovering new horizons beyond what we can see with the human eye, et cetera, discovering new paradigms for where we came from. But what is that which needs to be protected? It's the arts. It's like the culture of a civilization. And that needs protection. And one thing we do here at UC San Diego with this Arthur C. Clarke Center for Human Imagination that I'm a part of is to try to see what are the commonalities between the creativity of a scientist, the creativity of an artist, and a writer and a thinker. And what are those commonalities that can shed light on the meta level, on what does it mean to be imaginative, creative? And what you're saying a few minutes ago boils down to this pursuit of curiosity, which some say is our defining human characteristic.
Why are we here?
Yeah,
right?
Exactly. What makes us unique is that we have this capacity for curiosity. We're not just only obsessed with, well, how do we get more crop yield, or how do we get more termites to eat, or like other species might. So how do we and that quest beyond it, is what's so fascinating to me. And what makes us human, and the thing that I most want to understand in life is that urge.
Well, when we and then what sheds light when we're talking about this subject, right? Mm-hmm. Specifically space. Mm-hmm. Like, to me, I just start to question, like, why the fuck are we so concerned with all these mundane things? Yeah. What the Kardashians are wearing, what Donald Trump said or didn't say, or what it's like. Well, what about the fact that we're on a rock spinning through space? What?
Scale of all things, right?
Like, it's just we're here for a second. It's inconsequential, and then we're gone.
Absolutely.
It's mind-boggling to me.
You look up and you see 100 billion suns, burning away throughout the galaxy. And nobody ever looks up and says, I hate that star. You might say, I hate that Republican, I hate Trump, I hate Maxine, whatever. You could. But nobody feels politicized. I don't mean like the political aspects, as I said before. Global warming can be political, but I don't mean that. I mean science in its purest state as a search for new knowledge. It's not political, and that's what's so beautiful about it. We need, as a culture, a safe space where we don't have to debate and I don't say, "Oh, you're a Democrat, I'm a Republican, I'm a Republican." You want to have a safe space, and it could be that it's in sports, or it could be that. But nowadays, you even see with like sports is getting politicized. Like, I can't even read the newspaper. I don't care. I want to see a baseball game.
And it's just divisive
too. They make adversity in their lives.
Thank God science is still like that. Yeah, because they like conflict. Conflict sells. Conflict sells. You don't hear, today in wherever in Uzbekistan, this village that's been at peace for 100 years, still at peace. You don't hear about that. It's like it's not going to make the news. But science, I think, to the extent that it does make the news, I think it's usually it provides a reason for hopefulness, and I think that's ultimately science is the most optimistic expression of the human species.
And we were all born with awe and wonderment, not hate.
That's right.
And if we would just stop, like I'm camping this week down here in Carlsbad, and you just sit there and look up at the stars, and I just wish people would look up a little more often.
Right. It gives the cosmic perspective.
Yeah, definitely need to look up. When you say stars, like our sun could explode one day, right? Mm-hmm. Could cease to exist. Yeah. Is there anything that indicates that, like, have we measured that could happen, or that might happen?
Yeah. So we actually have a very well understood theory of how what's called stellar evolution, how stars are born, how they live out their lives, and how they die. The most important parameter that describes them is their mass. So the bigger the star, the more likely it's to burn out, blow up, explode, maybe turn into a black hole. In some cases, our sun.
You got to go back to black hole before you're done.
Our sun is sort of in an interesting state because it's the most familiar stellar object to us. We define everything either as being more massive than our sun or less massive than our sun. A star that's much more massive than our sun could explode in what's called a supernova. It could collapse. It could form a black hole potentially, or a neutron star. Our star, the sun, will probably not do that. It will probably swell up, get really large, cool off, become more red in color, vaporize the planets in the solar system so there's nothing left, eventually cool back down in what's called a white dwarf. But keep paying your taxes. I always think it's going to take about 4 billion years. The sun's about middle age right now.
How do we know that?
So we measure population. So we don't have we don't have a camera watching the sun, obviously, but what we do have is 100 billion other examples. Some are just like our sun. And we've seen how they evolve on what's called this sequence of stars, called the main sequence of stars. And so we make up in quality of data with quantity of data. So you can get a very accurate estimate of the lifespan of how long you're going to live, not from, I don't have to go into your genetics and find out exactly, well, you did this, you smoked this, and that great, whatever. I can just say statistically, there's, half the population, 3.5 billion men on Earth, and then I can drill down a little bit deeper and find out exactly, and that's how insurance companies make their money, right? They bet you're going to live for a certain amount of time, you're betting you're going to die. And so these statistics and actuarial statistics apply to stars as well. So we have a good sample of other stars that are similar enough to our sun that we can divine what it's going to be like.
You mentioned black holes.
So black holes occur when a star is about twice as massive as our sun. So it wouldn't look exactly like our sun. We wouldn't be here asking at this position from that object because it would be too hot for water to exist, for carbon-based life forms to exist. Maybe we'd be farther away from it. But so when a black hole forms, a star gets so massive that eventually, when it can no longer fuse its elements together to make the energy that is given off in nuclear fusion, that star collapses under its gravity, and it can form a supernova. And what's left over after the supernova, in some cases, can be a black hole. What is a black hole? A black hole is is defined as a place where gravity is so strong that not even light can escape from it. So in our case, or in the case of a very massive star that's tens of times the mass of the sun, it could actually collapse to a place where in a finite volume, maybe something bigger than our solar system, but not by that much, that anything that got within that distance of the center of this black hole would never be able to, not only would it never be able to escape, but light produced by it. So if you shot a laser beam right as you're falling into what's called the event horizon, that's the last signal anyone would ever see. They would never see what will happen to you if you're waving to them as you're going through the event horizon. They'll just see you eventually. You'll be frozen in space and time. You'll be frozen for all time in this whatever position you last went through this hypothetical surface or this boundary called the event horizon.
So when we look up at space and we see the space between stars, could that be black holes there?
There could be black holes there. There could be black holes there, and we wouldn't be able to see them because we have no backlight to compare against. So the way that we know that they're black holes, and we've seen black holes in a variety of ways, one way is that they do give off light, but not from themselves. So when matter falls into it, it's like a big disposal in your sink. When matter falls in, it gets heated up through friction, rubbing together, and it can get extremely hot. And there can be processes that give off very high energy X-rays and gamma rays and things like that. And it does so in a very complicated pattern, but we've seen the traces of these X-rays in space. We've also seen when two black holes come together, they give off the same waves of gravity, very similar to what I was talking about in the early universe's spark, this Big Bang gravitational wave background. The black holes that we've observed with this experiment called LIGO, that indicated to us that two black holes about 30 times the mass of the sun. So one was, say, 30 times the mass of the sun. One was like 32 times the mass of the sun. They came together and they formed a black hole that's 60 times the mass of the sun. So two solar masses worth of energy got converted into energy in the form of gravity. Because black holes are black. They don't give off light. So the only energy that they could give off are waves of gravity. And we detected those waves of gravity by the motion of a detector in Louisiana and one in Washington State. And they vibrated at just the right magnitude compared with what Einstein's prediction was. And it showed that black holes exist. And black holes can get swallowed into one another and create a new black hole that's more massive by just a little bit less than the sum of the two masses. And the missing mass comes in the form of energy in the waves of gravity.
So and what happens in a black hole? Does everything get destroyed?
Black hole is an incredibly mysterious place. We don't know exactly what happens once you go inside the event horizon, which is no matter because you could actually never go into one. We don't believe we could ever go into one. I know in Interstellar they have wormholes and they have black holes combined with one another. Part of the reason I do what I do, which is to build telescopes that actually can observe things, is that I like to kind of get rid of some of the nonsensical theories and maybe prove what's actually correct or observe what actually does exist. So wormholes are like really fascinating. They appear in movies, like I think A Wrinkle in Time and other things. But in terms of like, do we have any evidence for them? No, not right now. Black holes were sort of at that level about 50 years ago when they were first conjectured in the 1960s. But now we have abundant evidence for their existence, but we still haven't like been to one. We haven't made one. But you're absolutely right. There could be a black hole in the blackness of space that we couldn't see. We could detect it if it collides with something else using the waves of gravity approach. Or we could do what's called gravitational lensing, which is another consequence of Einstein's theory. There are ways to measure the existence of things that you can't see with light. And that's what's really fascinating.
Well, you say you don't think we could travel through one. What's your evidence that
what gravity really means is that there's black holes. Gravity really means is that so the typical analogy, which is only barely serviceable, is imagine they have like a trampoline and you put a bowling ball on a trampoline. So what a massive object does is it distorts gravity. It distorts the force of gravity that you'd feel. So if you got close to a black hole, you could have a black hole that has the same mass of the Earth. And if it was located 5,000 miles away from us, 6,000 miles away from us, you would weigh the same as you would on the surface of the Earth if you're near that black hole. But if you have a black hole that's much, much bigger, as you got physically closer, that would only occupy the space of, maybe of a proton size or something like that. It would be incredibly small. So you personally couldn't get into the event horizon to get ripped apart. But if you have a solar mass black hole,
ripped apart.
So something that's bigger than the mass of the sun by a factor of 2, you could actually get close enough so that, on a human scale, the force of gravity on your feet would be exponentially larger than the force of gravity on your head, even though it's only 6 feet apart, right? So that is like the force of tides on the Earth's oceans. That tidal force could be stronger than the chemical bonds that bind your atoms together in your body. So you could actually have a gravitational force, even though it's the weakest of all forces in general, specifically near a black hole, it becomes much more important then. So the matter that, let's say a planet was orbiting near a black hole, the planet's held together by chemical forces. It's made of carbon, silicon, iron. Those chemical bonds can get ripped apart by the gravitational field. So gravity has enough strength on black hole scales to totally obliterate matter and completely destroy matter. And when it does that, the black hole gets a little bit bigger. So it's kind of like the blob. When it eats something, it gets actually bigger, physically larger, and more massive.
So is it taking on energy, 1, and then 2, if energy can't be created nor destroyed,
right,
is a black hole a Big Bang on the other side?
Yeah. So some people do speculate that the universe could come from something that is allied with a black hole, and that's called basically a white hole. These two things together are what are both known as singularities. So you might have heard the word singularity or whatever. Singularity means that you're dividing something which is macroscopic, like something bigger than 1, or even if it's not bigger than 1. You're dividing it by 0. You're saying how much mass in the numerator divided by how much volume in the denominator. That's density. When you make the volume 0, you're dividing something macroscopic, a mass of your mass, kilograms, or the Earth's mass. You're dividing that by 0. So you get in singularity is a division by 0. So you get infinite density. So we actually don't know what the properties of the matter are like when they're in that state at the center of a black hole. And it does depend on the size of the black hole. But we do know that the size of the black hole would change, the area of the black hole would change depending on how much matter it's gobbled up. So, and we do see the remnants, as I said, of 2 black holes coming together to make a third black hole, and then those 2 black holes that were previously there do no longer exist. But really, you can only think of them as a gravitational structure. You can't think of like, well, there's people in there, or there's atoms in there, and you really have to think about it as this is the force of gravity that an observer would feel if they could weigh themselves. Or you could put a scale there. How much would the spring in a scale deflect as it got closer and closer to the event horizon and then beyond the event horizon? And then the other thing is that the gravity can be so strong, it's like the bowling ball's mass going to infinity rips the trampoline, but preserves it. So you need an infinite amount of energy to climb out of it because the gravitational field is so strong. So we see effects of the boundary between the outside the black hole and the black hole's event horizon. We see those effects, and we see the collision of multiple black holes. But beyond that, we don't really, there's some thought of, well, you could make a black hole if you have enough energy in a small enough space. Those fears were unfounded. They weren't able to do that.
You say we're kind of at the precipice of understanding a black hole.
Yeah.
What do we see them in
Turns out
telescopes?
they're very. So you can see the effects of them. We believe at the center of our galaxy, and every massive galaxy like ours that has hundreds of billions of stars, perhaps, that they're orbiting. All the stars seem to be orbiting around basically a blank spot where there's no star at the center of our galaxy.
This is
This
one
our
or
galaxy.
multiple.
No, it's one black hole. We think there's just one black hole at the
You
center
think
of our galaxy.
we only think there's one black hole,
But it's a million
in
times bigger
our
than our
galaxy.
sun, the more mass than our sun. So it has a million masses of the sun concentrated into a region smaller than our solar system, closer to us than Neptune. So it's an amazing amount. Imagine a million stars, would be, the sun
So
is
there's
a million kilometers in
something.
diameter.
How far away is this?
So the center of our galaxy is about 60,000 light years away from us. So it's fairly far
It happens
away
to
from
be
us.
in the center.
It happens to
what
be in the
appears to be the center? Or is it the
Exactly.
center?
Yep. No, it is the center. So we see stars. So another reason we know it exists, we see stars orbiting around an empty place in space. So there's nothing there. You don't see like a shadow. If you were close enough, you would see a shadow. And you'd see all the light rays that were coming from right behind it would be refracted like a lens. But you'd see a disk, the black disk, and then surrounding would be this halo of all the light coming to us from beyond the black hole. But anyway, so the black hole that is at the center of our galaxy is causing stars to orbit around it, just like the planets in our solar system orbit around the sun. So if you turn the sun off and you kept its matter there in the form of a black hole, the Earth would keep orbiting around it. Mercury would keep, or we would all die eventually because we would have no solar illumination. But nevertheless, the planets would keep orbiting just like nothing ever happened. Only if you just got rid of the sun altogether would the planets fly out of their orbits. So the stars are orbiting around this dark star that we can't see at the center of our galaxy, and we take pictures of those stars using infrared light.
And what's happening to those planets? Are they eventually being stars?
Some of them are getting ripped apart if they go close to the sun, like a comet when it goes close to the black hole. Some of them are getting ripped apart into gas clouds and planetary kind of nebulae. Those objects, some of those are going to crash into the black hole's event horizon in the next 10 years or so. So there are telescopes.
You already know this is going to happen?
Well, it's just like we know that Mercury is going to be over there tomorrow. Yeah, so we do know that. So we can predict the orbits based on the theory of relativity and even Newton's laws and Kepler's laws, which go back 450 years. We can predict very accurately where those stars are going to be orbiting around the black hole. All you need to know is what the mass is. And that's how we measure the mass as well, from the orbital dynamics of the stars that surround it.
How long have we been watching this black hole?
So there's movies you can look up online. There's a colleague of mine at UCLA named Andrea Ghez. She runs a group that looks at the center of the galaxy using these very interesting telescope techniques that can get rid of the atmospheric blurring, the scintillation, the twinkling of starlight. She can look and peer into the center of the galaxy using a telescope on Mauna Kea in Hawaii, and she can see what's happening to these stars over years. And she's been measuring them since 1994, I think. So she's got, and some of them go around the black hole every 3 or 4 years. So some of them are orbiting pretty fast. And she can peer into the center of the galaxy. She can see dozens of stars moving around the center, and she can predict when fragments of those stars are going to break off and fall into the black hole. So far, every time they predicted, and I think it's partially to get publicity. Every time they predict, there's going to be a big, it's basically like a forecast, and they keep getting it wrong. If nothing ends up being visible, eventually something will happen. I'm pretty confident about that. And when that happens, I predict she'll win a Nobel Prize. But that could never happen. It could happen tomorrow. We don't know.
That's awesome.
Yeah.
Wow.
So cool what we know.
Yeah.
And what we don't know.
So isn't that cool? Like, if we knew everything, it would be boring.
Yeah.
Right?
That's right.
The wonder we talk about.
What would Brian do all day long?
Yeah.
I mean, we could still make movies. You could still make movies, but
Yeah. Tell stories.
There is a movie called The Black Hole.
Yeah, the wonder, man.
Definitely.
Have you seen this?
Which
it's
one?
Neil Tyson posted the first computer. What does it say?
Computer-generated image of a black hole.
Let me see
Eastwood.
this thing. Let me see this.
So yeah, when they talk about how they generate an image, they're constructing what the force of gravity would look like at different points around the black hole, or it could be around anything. You can actually, the gravitational field of view is actually interesting and complicated to look at.
Yeah.
Black holes are actually pretty simple. They only have 3 properties. They have mass, they have how fast they rotate because they can actually spin, and they have charge. They can be charged, we think. We actually haven't observed their charge necessarily, but we've observed their mass and their spin, and then the spin can point in 3 different dimensions, so it can point in. So really, they're very simple. It's sort of like an atom, or not even an atom. an electron. You've seen one electron. People never say, "Oh, electrons are so fascinating." Like each one is identical. They're all commodities. It's like a grain of corn or something. You know, like they're all the same. They just have, you know, they matter in aggregate, not individually.
Wow. Well, I got no more questions. Only 1,000.
1,000 more questions.
Yeah.
We got
I think that's enough for today.
Yeah. You guys want to check out the laboratory and the telescopes?
Yeah.
Thanks for your time, bud.
I'll show you guys our detectors, our telescopes, we have all sorts of really interesting things. And our claim to fame is we have the coldest spot in San Diego and all of California, probably. We cool things down in our laboratory to not even 1 Kelvin, 1 degree of absolute zero. We can cool it down to 6/1000ths of a degree above absolute zero.
Let's go check it out.
Yeah.
So cryogenics, kiss my ass,
That's
right?
Yeah, don't go into the cryo machine. I only charge $1,000. Thank you guys very much.